Hello, hello. Welcome back to another episode of Engsci Recap, where today I will be going over CHE260, Thermodynamics and Heat Transfer. My name is Jason. I just finished my second year of engineering science at the University of Toronto. And yeah, let's get right into it. So CHE260 is a course I took in my second year in my fall term, and I had Professor Sanjeev Chandra. This course, it was split into two parts, as most of our courses were in second year. So the first half of this course covered thermodynamics, and the second half covered heat transfer. And the way it was explained to us was sort of the difference between the two is heat transfer really cares about how heat flows, I guess, over time. So we dealt with a lot of time dependence, whereas in thermodynamics, we don't really care about how exactly we get from an initial state to a final state. We sort of just care about sort of those endpoints in time. So in the thermodynamics section of this course, we covered, of course, the ideal gas law. We do a lot of steady state analysis, again, because we don't care about time dependence like we do in heat transfer. Talk about enthalpy, specific heat, steady flow devices. We also do some control volume analysis, entropy, as well as isentropic processes, phase change and phase diagrams. The Carnot cycle was touched upon briefly. And for the heat transfer section of this course, we talk about heat transfer mechanisms. So that would include stuff like conduction, convection, radiation. We talked about thermal resistance networks, which are analogous to the resistance networks you would find in circuits. We have heat conduction in plates, cylinders, and spheres, thin surfaces, transient heat conduction, forced convection, thermal boundary layers, radiation heat transfer, and gray surfaces. So today I wanted to go over a question from the first assessment I took in this course, actually. It was quiz one, question two, which I wrote very early in fall term, September 30th, 2021. And this question covers, of course, ideal gas law, work done by a gas, internal energy, and heat transfer. So this is the question. There's quite a bit of reading to do, but essentially we're given a cylinder. Uh, we're given the dimensions of the cylinder, and there is a piston at the bottom, and this piston separates some air at the bottom of the cylinder, and there is water on top of the piston. So basically, the idea of this question is we're heating up the air at the bottom of the piston. And, intuitively, when you heat up air, it expands. And basically, the question is, uh, once we've heated up the air enough so that it's expanded to a point where the piston is at the top of the container, which means that all the water has spilled over the sides, we want to find how much thermal energy we've transferred to the air in order for that to happen. And we're given a bunch of constants. We're given atmospheric pressure and acceleration due to gravity, the density of water, and these are all sorts of hints as to how we could approach this problem. Other important values were given. So we're given a bunch of initial quantities. So for example, the initial temperature of the air, the initial volume of the air, um, the the temperature of the water. I don't believe that's actually important, but uh, let's dive right into this question. So how exactly do we approach this problem? Well, the most important observation we should make is that the pressure of the air is going to be linear with respect to its volume. And you might be wondering, okay, like how can we see this sort of intuitively? Well, what we can argue is that the volume of the air is going to be proportional to the volume of the water. And this makes sense because any time we increase the volume of the air, the volume of water in the cylinder is going to decrease by just as much. It's a 1-to-1 ratio because the cylinder's volume is constant. Because of this, we should also realize that the volume of water is linear with respect to the mass of the water. This is quite intuitive. They're related by the density of water. We should also notice that the mass of the water is related to the gravitational force that is exerted on it by the Earth. And this force is linear with the pressure experienced by the air, because essentially the pressure of the air at steady state is going to be equal to the pressure exerted on it from the other side of the piston, right? Otherwise the piston would be moving and we're not at steady state. So at steady state, the pressure of the air would be equal to the pressure exerted by the water due to its weight, as well as the atmospheric pressure. So these quantities are all related to each other in some linear way. And we can see if we take the first term, the volume of air, it's related through this chain of proportionality. It's proportional to the pressure experienced by the air. And this is going to be really important. The other thing we should notice is that because this is thermodynamics, we should define an initial state, state 1, and a final state, state 2. So state 1 will be the case where we have not begun transferring heat to the air, and state 2 is going to be when all the water has been displaced. Some useful equations we want to use for this question include the ideal gas law, obviously, rewritten in terms of mass instead of number of moles, and replacing the gas constant with that of air. We want to use the work equation for the amount of work done by the gas. So that would be equal to minus integral PdV from the initial volume to the final volume. We also want to use the change in internal energy equation, which is dictated by the change in temperature, the mass of the air, as well as the specific heat at constant volume. We also want to use the heat transfer equation, which basically says that the amount of heat we've transferred to the air is equal to the change in internal energy minus the work done. So we want to use these, and ultimately the quantity the question is asking for is Q12. So this is a visual representation of the proportionality I was talking about earlier. As I was saying, the volume of the air is proportional to the pressure, which means that there is a linear relationship. And this is going to be very important when we want to calculate the work done by the air. Because intuitively, we know the air has to do work on the piston in order to displace all of that water. And the way in which you calculate this is using the work equation. But in order to calculate this integral, PdV, we can notice from the PV graph that this area under the curve is simply a trapezoid. So we can use our formula for the trapezoid, which is 1/2 P1 plus P2 times V2 minus V1. Again, the subscripts just represent final versus the initial. So 2 represents the final state and 1 represents the initial state. So this is how we calculate the work done. We should remember that P2 is going to be equal to the atmospheric pressure, which is given in the question. The reason for this is that there's no more water on the piston. All of it's been displaced in the final state. And V1 is given to be 0.3 cubic meters, and this is for the air. V2 is going to be the entire volume of the cylinder. We're given that it has a height of 10 meters and a cross-sectional area of 0.1 square meters. So that means the total final volume will be 1 cubic meter. The volume of water would simply be the difference. So that would be 0.7 cubic meters. And this is during the initial state. And the reason we want to know how much water there is because we want to find the initial pressure. And the initial pressure, as I mentioned earlier, is going to be the sum of the pressure exerted by the weight of the water plus the atmospheric pressure. So we know the volume of the water, we know the density of water. Again, we were given the temperature of water in the question. That's not super relevant. It could have some impact on the density, but for the purposes of this question, we don't really care about that. We just say 1,000 kilograms per cubic meter. So the total mass of water is 700 kilograms. And to find the force exerted by it, we just have to multiply this by the gravitational constant, which is 9.81 newtons per kilogram. And to find the pressure, we divide it by the cross-sectional area of the piston. So P1, which is the initial pressure, is going to be P2 plus this pressure exerted by the water, and we get something like 170 kPa. So now we know P1, P2, and V2 and V1, so we plug in all our values, and we find that the work done is approximately 95 kilojoules. So this is the work done by the air. Now we have to calculate the change in internal energy. So we know CV and the gas constant for air. These are all table values that were given as part of the test. We're also given the initial temperature, which is 300 Kelvin, but we need to find the mass of the air, which it's not something that we have. So we want to use the ideal gas law. We know all of these quantities already because they're given, and we had calculated the initial pressure in the previous section. So we find that the mass of air is approximately 0.59 kilograms. Then we can use the relation PV over T is equal to a constant. So we can relate the final quantities to the initial quantities. So we find that we can derive an expression for the final temperature in terms of quantities we already know. We already know P2, V2, P1, V1, and T1. And we find that the final temperature would be 596 Kelvin. So this equation we could simply derive from the ideal gas law. You would get PV over T is equal to mR because the mass of the air never changes due to conservation of mass, and the universal gas constant for air does not change. This would be the same value whether we're in the initial or final state. So now that we have T2 and T1 as well as M and CV, we plug those into our equation and we find that the change in internal energy is approximately 126 kilojoules. And finally, we can plug this all into our equation for Q12, which is the difference between these two values. And notice that because we're subtracting the work done by the air, this becomes a positive value. So the change in internal energy is not representative of all of the heat that we needed to put into the air. We actually needed to put additional thermal energy in order to provide work to displace the water. And that's why the final answer is around 220.5 kilojoules, and this is more than the individual components of the work or the change in internal energy. So before I end up this video, I'd like to make some quick acknowledgements. I'd like to thank Professor Chandra for the course and the quiz content. I'd also like to thank my tutorial TA for the thermodynamics section, Surya. And I'd like to thank the individuals who helped make this Beamer template. But yeah, thanks so much for watching, and I'll see you in the next video.